I want to talk today about what happens when we take an inductor and we hook it up into a DC circuit. So kind of like what we have here. So what would happen in this DC circuit is when we would close this switch, enter it as the source, our DC voltage, our voltage would start immediately. So we would get voltage, right? Close the switch, there's 24 volts or whatever it may be flowing in the circuit. Well, we know with inductors, they're opposing that change in current. Well, as soon as I close this switch, current is going to try and go from 0 to whatever my value of current is. So we're changing the value of current. Because we're opposing that, what we see is a rising arc of current. So we see something like this happens with our current. Now, it's important to understand that, yes, we're seeing this opposition to a change in current due to inductance, but we're also seeing the resistance in the circuit. Our coil of wire is going to have resistance in it, right? It's just wire. That resistance is what's actually keeping the current at this steady state, at this level. So it's important to still understand that in this case, our current is still going to be I equals E over R. All right, so the resistance is still telling us what our current is. It's just that inductance that's making our current go up like this. Now, there's two things we got to talk about here. Well, what happens is as it's rising from 0 up to what we'll call a steady state, it takes 5 equal amounts of time. So what we call these is we call these time constants. So there's one time constant, we'll call it TC1, TC2, TC3, TC4, and TC5. So there's 5 equal time constants, and they're the equal amount of time in each of them. So what happens? It rises up. We end up with a relationship. So we end up with a very important relationship, which is the time of one time constant in seconds is equal to the inductance in the circuit, right? The Henry rating of our inductor divided by the resistance. So the more inductance we have, the more opposition to changing current, the longer it's going to take. The more resistance we have, the less time it's going to take because it doesn't have to rise so high. So we need to understand that relationship. It's an important. Just keep in mind this is the time of one time constant. If we were looking for 3 time constants or 5 time constants, we could take T equals L over R and then times 5 to get the total time. So 5 time constants total. So in addition, this relationship is extremely important, but what we also see is we see this current rising on a curve. Now this curve is always going to act the same way. In the first time constant and one time constant, it's going to rise 63.2%. Every time it's going to go up from 0 up 63.2% of its total value. That's in TC1. Now by the time it reaches the second time constant, what it's doing is it's going to increase 63.2% of whatever's left. So of the 36.8% that's left, it's going to rise 63.2 of that. So what we end up with is 86.5% of the total at TC2. Then it's going to rise 63.2% of whatever's left, which takes us to 95% of the total, which is TC3. Then it's going to go up to 98.1% of the total, TC4. And by the time it reaches up here, we're at 99.4%. And for us as electricians, we say 99.4% is close enough. We'll call that steady state. So keeping in mind each time constant, it's rising up 63.2% of the value. So hypothetically in this case, if we were talking 10 amps, right? If we were talking 10 amps was our steady state current, we would be after one time constant 6.32 amps. After 2 time constants, we would be 8.65 amps. After 3 time constant, we would be 63.2% of what's left. We would be 9.5 amps. Then we'd be 9.81. amps and 9.94 amps, right? So this is that relationship, and that's how it works. What we do have, if we want to use it, is we do have a formula that can help us out. I think these numbers are the most important, right? 63.2% rising in each time constant. But if you want, you can also go current of a time constant. So if we're looking for one of these values, equals the steady state current, 1 minus e to the negative time constant. So let's say we were looking for this guy right here. We could go I of TC3 equals 10 amps, which is our steady state current, 1 minus e to the negative 3, because we're looking for that third time constant, and it should give us 9.5 amps. Well, I hope that helps. Thanks a lot for watching. See you again soon.